Welcome back to another explainer. So, if you've been tracking the wild, rapid advancements in embodied AI lately, you know that vision language action research, or VLA, is moving fast, like breakneck speed fast. But there's a catch. We're facing this massive fragmentation problem. Basically, everyone is building these incredibly cool robots, but nobody is sharing the instruction manual. Well, today, we're diving into a groundbreaking new codebase that completely solves this. It's called StarVLA. The authors of the paper actually describe the current state of embodied AI as a Tower of Babel. And honestly, that hits the nail on the head. What they mean is you have these brilliant researchers all over the world building absolutely incredible things, models that can see, reason, and act out in the physical world. But they can't speak the same technical language. They're stuck using completely different code bases, making different interface assumptions, and relying on entirely disjointed testing protocols. It's kind of chaotic. So how exactly do we tear down this Tower of Babel? Well, here's our roadmap for the explainer. First, we'll look at the VLA Tower of Babel. Second, StarVLA, Lego for robotics. Third, backbones and action heads. Fourth, flexible robot training recipes. Fifth, putting StarVLA to a test. And finally, number 6, a unified robotic future. Let's get into it. Starting off with Section 1, the VLA Tower of Babel and the chaos of fragmentation. Right now, the field is largely split into two major camps. On one side, you've got VLM-based methods. These take those massive, powerful vision language models and repurpose their language-generating abilities to actually decode physical actions. Then, on the flip side, you have world model-based methods. These use generative architectures to predict future observations and physical dynamics. The problem? Because these two sides use completely incompatible codebases and testing setups, it's pretty much impossible to fairly compare them. You can't just casually swap one out for the other to see what works best for your specific robot. Moving right along to Section 2, StarVLA, Lego for robotics. This is all about a modular, backbone, action head architecture. The researchers behind this paper realized something crucial. We don't need just another isolated model. We need a standardized foundation. And that brings us to what StarVLA actually is. Think of it like a universal Lego set, but for robotics. It's an open-source platform that essentially forces both those VLM-based and world model-based paradigms into one shared modular framework. By treating the core foundation, the backbone that understands the world, and the action decoding parts as completely independent, interchangeable Lego pieces, researchers can finally start mixing and matching. To really picture this ecosystem, imagine a unified pipeline. Over on one end, you have a shared data flow. Right in the middle, a standardized model forwarding framework. And on the far end, a unified testing protocol. By standardizing the outer boundary, which is just how raw observations become actions, and the inner boundaries between the backbone and the action head, StarVLA creates this brilliant bidirectional modularity. Basically, you can swap out a vision language backbone for a world model backbone, or swap a simple regression head for a complex diffusion head. And the best part? It doesn't break any of your surrounding training or evaluation setup. All right, Section 3, backbones and action heads. Let's see how we actually snap these pieces together. So, what exactly can we build right out of the box? Well, StarVLA currently supports 4 very distinct action heads, which cover the major decoding families out there right now. First up is StarVLA Fast for autoregressive tokenization. That's essentially treating physical actions just like next word prediction. Then we've got StarVLA OFT for straightforward parallel continuous regression. If you want to dive into generative models, StarVLA Pi offers flow matching denoising. And lastly, StarVLA GR00 brings in a complex dual system reasoning approach. And the kicker, all of these share the exact same interface. Now, this is where the magic really happens. Because of that unified interface we just talked about, you can take any of those 4 action heads and literally snap them onto entirely different foundations. You want to use a vision language model like Qwen3VL? Go for it. Prefer dropping in a world model like Cosmos Predict 2? You can do that too. Have you ever wondered if a diffusion head works better on a VLM or a world model? Well, for the first time, you don't have to guess. You can actually test it in a perfectly controlled environment and isolate the exact effect of your design choices. It's a real game changer. Which brings us to Section 4, flexible robot training recipes, or learning from diverse data streams. Okay, so you've got your custom robot model built from your Lego pieces. Now, how do you actually teach it? Historically, training these robotic models meant dealing with incredibly messy, bespoke scripting. It's a nightmare.
StarVLA fixes this by treating training strategies as reusable configurations rather than custom add-ons that take weeks to write. You get a unified infrastructure for supervised action learning, that's your standard behavior cloning, but it also supports multi-objective code training. That means you can mix robot action data with web-scale vision language data, so the model doesn't suddenly forget how to reason while it's learning to move an arm. It even handles cross-embodiment pre-training, letting you train on a mix of completely different robots. And every single one of these recipes applies no matter what backbone or action head you picked.
Let's move to Section 5, putting StarVLA to the test. Let's validate that efficiency and performance. Look, modularity and unified training sound fantastic in theory, right? But they don't mean much if the models can't actually hold their own against the older, tightly coupled methods. Well, when put to the test on the Libero manipulation benchmark, which is a very standard tabletop robotics test, StarVLA absolutely delivers. The existing OpenVLA OFT model hit a 97.1% average success rate. StarVLA OFT, built entirely using this new modular framework, matches that state-of-the-art performance with a super close 96.6%. But hold on, you have to look closely at the training steps here. OpenVLA took 175,000 steps to get there. StarVLA? Just 30,000. Let that sink in. It achieves top-tier performance with 6 times fewer training steps. That is an absolutely massive data and computational leap for this field. And those gains aren't just a fluke on one single benchmark. It completely dominates in complex simulated proxy environments, like simpler ENV2. Using the WidowX robot visual matching setup, older models like OpenVLA really struggled, barely scraping above a 4% success rate. Even stronger recent models like CogAct topped out around 51.3%, but the StarVLA GR00 configuration, it scores over 65% success. It's giving us an incredibly strong baseline straight out of the box, literally just by standardizing the architecture. Best of all, taking this model from a simulation and deploying it to a physical robot in the real world is stunningly easy. We're talking 0 code changes to the core framework, none. You just run this super rapid 4-step server-client loop. 1, the robot captures a camera observation. 2, it assembles that into a standard data dictionary. 3, it pings the remote policy server. And 4, it executes the returned action on its actual hardware. The model honestly doesn't care if the observation came from a simulator or a real camera. It just processes the data and sends the command. And finally, Section 6, a unified robotic future and the generalized VLA perspective. So we've seen the architecture, we've seen the crazy efficiency in the data, and we know how easy it is to deploy. But what does this all mean? Well, StarVLA does something profoundly important beyond just being a neat engineering tool. It suggests what we call a generalized VLA perspective. It essentially proves that those fiercely debated methods of the past, the whole VLM-based versus world model-based rivalry, aren't actually fundamentally different. Because they can both run smoothly through the exact same modular pipeline, they're really just different inductive biases operating under the exact same structural umbrella. When you strip away the differences in the infrastructure, the underlying commonalities are absolutely undeniable. And that leaves us with a pretty fascinating reality. Now that the Tower of Babel has fallen and been replaced with this universal Lego set, researchers are finally speaking the exact same language. The barriers to entry and the barriers to experimentation are lower than they have ever been. So the only question left to ask is, what are you going to build next with these standardized pieces? Thanks for hanging out with me for this explainer. Keep exploring, keep building, and we'll catch you in the next one.